Hi, my name is Joshua Sachs. I'm Chief Data Scientist at Sophos, and my talk today is entitled Deep Neural Networks for Hackers, Methods, Applications, and Open Source Tools. So just to humanize myself a bit, this is me on the left with my daughter Maya and my wife Ksenia. It's me playing piano. It's a book I just finished on the plane, Man and His Symbols by Carl Jung. Another book that I liked, Galaxies by John Gribben, about the natural history of the universe. And then all this is a setup to justify this plug, Malware Data Science. This is a book by Hilary Sanders and I. Hilary and I worked together at Sophos, and we wrote this book. It's sort of an expansion. If you guys like the talk, I'd recommend checking out the book. It's going to be available later this month. You can pre-order it on Amazon. So this is the team I work with at Sophos. That's me on the upper left, and then in order in which people appear: Maddie, Rich, Hilary, Adarsh, Constantine, Ethan, Felipe, Alex, Cody, William, Matt Steck, and Matt Burnett. My team's all here up in the front row. Please come talk to us after the talk. Everybody on this slide contributed in some way to this talk and to the research that went into the talk. So I'm giving the talk, but want to give credit where it's due. I put you on the lower right. If you're interested in security data science, we're hiring, so feel free to talk to us. Okay, so broadly, my talk today is focused on security data science. Narrowly, it's focused on neural networks. Neural networks, as a phrase, is synonymous with deep learning, deep neural networks. I'm going to use those phrases interchangeably throughout this talk. But I wanted to situate what I'm talking about today within the larger context of security data science. So that there are, at least in my view, there are three areas of security data science. There's machine learning. So these are algorithms that learn to solve problems from data. So a good example is a malware detector machine learning system, which is trained on training data, so known malware, known benign-ware, and learns to detect new malware, right? That's machine learning. There are multiple areas of machine learning. Neural networks is one. There are other areas like decision trees, which are commonly used in the security industry. I'm going to argue today that neural networks are the most exciting and most important area of machine learning right now. It's where most of the research effort is being focused and where most of the breakthroughs are happening. But there are other areas of machine learning I'm not covering. I'm not going to be talking much about data visualization. Data visualization are algorithms that render complex data in ways that allow the human eye to recognize patterns, outliers, and trends. Another area would require another talk. And databases are also quite important to data science, but I'm not going to be focused on that today either. Okay, so what's deep learning? I'm going to start by defining it in terms of applications. So this is a really cool application of deep learning that I would say would not be possible without deep learning and deep neural network technology. So what you're seeing here is a neural network that in real time is recognizing a whole range of objects in a James Bond video clip. So the neural network is running on about $1,000 worth of hardware, so not that expensive. And it's identifying these bounding boxes around the images at 30 frames per second, so very quickly. And it's doing it really accurately compared to non-neural network approaches to solving this problem. So this is super important, right? It's quite a breakthrough that we can do this today. And it's only really in the last decade that we had machine learning technology that could recognize objects this quickly and this accurately. And it's really due to developments in deep neural networks that I'm going to be talking about today. So I'm going to introduce you to the math behind this kind of neural network and show you guys how it applies not only to computer vision, but also to security. So without this kind of breakthrough, we wouldn't be talking about self-driving cars and robotics applications that have to process video feeds in real time. Here's another example of a computer vision neural network which also learns to control its environment. So this is a demonstration of a neural network that's learned to play Super Mario Brothers. The special thing about this, there have been AI systems in video games for a long time. This is special because the neural network is just looking at the pixels coming off the video card of the SNES emulator. And it's learned from scratch to understand the video feeds, right? To manipulate the controller, to manipulate Mario on the screen. It's learned what the power-ups look like, what the enemies look like, and it's learned to play the game, right? So this is a toy. It's not super useful to play Super Mario Brothers, right? But this kind of learning, which is called reinforcement learning, is super important to robotics applications and other applications, and we're still looking for ways to apply it in the computer security industry. Last example I'm going to show outside of the world of cybersecurity are neural networks called generative adversarial networks, which generate content. So this neural network on the left here has been trained on a large database of celebrity face images, and it's learned to generate new celebrity face images. So the images I just showed you are not real people, right? They were imagined up by a neural network which has learned to generate them. And these are not real photos, right? These were sampled from a generative adversarial network, so this content was created by a neural network. So it's not totally obvious, the application of this, right? But you could imagine in a security context, using generated content like this to populate millions of fake social media profiles, right? Which you could then use to go wage a disinformation campaign. And there are other applications of these kinds of neural networks as well. On the right, I'm showing source code that was generated by a neural network. In this case, we're using the researcher who generated this used a recurrent neural network. So this source code probably wouldn't compile, but it is an example of just how well neural networks can understand the structure of language, both spoken language, textual language, and programming languages. So everything I've just shown wouldn't be possible were it not for the developments in neural network technology since around 2012. This is all new stuff. And it's all because of developments in the deep learning arena. Okay, so how does this all apply to security? So to start to make my argument about that, I'm going to show you guys a demo of a neural network that we built on the Sophos data science team. So this is a neural network that looks at URLs. The setup is quite simple, right? It looks at a URL, just the URL, not the HTML that it points to, and it assigns it a threat score. So the score ranges between 0, which means the neural network thinks that the URL is totally benign, and 1, where the neural network thinks the URL is extremely malicious. So I'm going to show you guys a demonstration of how this works once the video plays. Let me see. I need to click over here, I think. It's odd. Here. Let me try to fix this 1 second. There we go. Okay, so here I'm entering text into the text box, and we're going to see the neural network score the URL that I'm entering in real time. So I typed in Google, right? Thinks it's benign. Okay, so here are some examples just to show you guys the neural network doesn't, generate a ton of false positives. So that's CNN, Stack Overflow. Some random stuff, indeterminate, hard to say if it's malicious or benign. Now I'm going to start making up some fishy looking URLs, right? PayPal password recovery dot some random string.com, right? So the neural network has never seen this URL before, but it recognizes it's malicious. And the reason it can recognize it, right, is we've trained the neural network on 125 million URLs, about half of them known bad and half of them known good. So it's learned to recognize patterns in URLs that are suspicious. Now I'm permuting the URL, right? I'm changing spellings, right? I'm changing the randomized suffix, right? And the neural network's determination is invariant to these transformations, right? Now I'm using a non-random suffix, testdomain.com. The neural network continues to recognize that it looks suspicious, right? And you can think of the neural network as having learned to simulate the intuition that an experienced cybersecurity practitioner brings to bear in looking at a URL and deciding if it's suspicious or not, right? It's not always clear from a URL string if it's malicious or benign, but this neural network model does a pretty good job of squeezing the most inferential power it can from the information that's in the URL string. So I want to emphasize, I think this represents a different way of doing detection in our field. So still in the security industry, the main way we protect users from web-borne threats is through blacklists, right? So people subscribe to threat intelligence blacklists that give known bad URLs, and signatures that are basically regular expressions, right? So people see that there's a new web-borne campaign, and they write a regular expression to detect it, right? And we deploy those regular expressions to detect malicious software. Those methods are important, right? I'm not an AI practitioner who believes that we should throw out those old methods, but methods like these, like what I'm showing here, can augment those technologies. So you could imagine an application driven by this neural network, right, that shows you the top 20 most suspicious URLs that were seen on your network that were not detected by your existing technologies, right? And it's a way of focusing in on the huge haystack of URL data, right, around the stuff that is most suspicious, right? So it automates the process. In a way, it automates what a human does when they look through a huge log of URLs, right, and finds you the most suspicious stuff. I also want to sort of substantiate empirically why I think deep learning is important. So this is a chart that we actually generated internally that we use to monitor the efficacy of a malware detection product that we have that came out of our research group. So I'm showing 3 different time series here. So on the x-axis we have time, right? So I'm looking at the detection rate of this product from June through July. This yellow line shows that using non-deep learning technology, so sort of traditional signature-based approaches, right, we can achieve a pretty good detection rate of like 80–85%. Using just a neural network, we can achieve about 94–95%. And then using the 2 technologies together, we get up towards 96–97% detection rate. So we're cutting in half using a deep neural network, right, the number of malware samples that we miss, which I think is quite significant. It's not a silver bullet, right? It doesn't, I mean, you'll hear vendors claiming that it is. It's not, but I would say it's necessary. It's table stakes at this point if you're going to do malware detection to use some kind of machine learning approach. I'd argue neural networks are the superior approach there. So we've found in my research group, but also I think this holds for other security vendors and also large security operations centers. We found that machine learning is just an indispensable tool, and specifically neural networks. So we've developed, so here on this slide I'm showing architecture diagrams for neural networks that we've developed. You see on the left a HTML neural network, a Windows PE detector, which detects malicious EXEs and DLLs and sys binaries, an Android neural network, and a neural network that operates on file paths and registry keys. So we're using neural networks very widely. Actually, this is just a subsample of the systems that we've built to detect malicious content. So what we're finding is, I mean, not by virtue of some ideological commitment to machine learning, but for practical reasons, right? We need to use machine learning in all these contexts. It's a really important tool for detecting malware and detecting malicious behavior. So just to sum up, so in the old world, people use blacklists and signatures, right? Those are still important. They require a lot of maintenance. You need to send out updates once a day or multiple times a day to your customers. If you're a security vendor, right? If you're a user, you need to make sure that those updates are getting through to your endpoints and firewalls and security deployment. And we couldn't detect a lot. We weren't as good at detecting new malware, right? In the new world, we're using machine learning, neural networks to detect malware and malicious behavior, and we're able to be much more efficacious. And I think it's the 2 combined that are where we need to go as an industry. So neural networks aren't always effective, right? So this is the product of a recipe generator neural network. I suppose it's subjective whether or not you think this is a success. I'm a vegetarian. I guess this gelatin is not vegetarian, but anyways, probably not the best neural network outcome, right? Beef soup with swamp peef and cheese. I'm not even sure what peef is, but this is also the output of a neural network recipe generator. And just because I'm about to throw a bunch of really dense subject matter at you, just bask in the dopamine of looking at these cupcakes for a second. These are not the product of a neural network. Okay, so take a breath, and I'm going to get into the more mathy part of the talk. I'll say I was disciplined about not introducing any equations into this talk, but I am going to try to give you guys some intuition around how machine learning works and how neural networks work. And I'm hoping you're going to come out of this next section of the talk with a much better grip on deep learning and sort of a demystification of deep learning. Okay, so I want to start by talking about how the basic setup for how all machine learning detection works, right? So what you're seeing here is a plot of a bunch of training data. So let me describe this toy example, and I think it'll make sense. So suppose you want to build your own machine learning malware detector. So to start, you gather a data set of known bad and known good binaries. Then you extract some attributes from them. So in this case, this is, again, a toy example. I just made up the data. But let's say you extract how compressed is each file, how many English language printable strings are there in each file, and how big is each file, right? So with these three attributes, I can actually plot my data in a three-dimensional space, which is what I'm doing here. On the lower left, I have the malware, right? On the upper right, I have the benignware. And you can just look at this data, and your visual system picks up a simple pattern, right? The malware is in the lower left of the space, and the benignware is in the upper right of the space. Now, this space we're talking about is called a feature space. It's the space that's implied by these three features: compression, printable strings, and file size, right? And we look for patterns in the space, and we can see this is a simple pattern. Now, the math problem here, the machine learning problem here, can be posed as, how do we find a separating boundary, which we call a decision boundary, that captures that pattern, right? So that green plane in this plot is a machine learning decision boundary, right? So the idea is, if I see a new binary, and I don't know if it's bad or good, if it's on the upper side of the plane, is it bad or good? It's good, right? If it's on the other side of the plane, it's bad, right? And so, I mean, there's some intimidating math that goes into identifying that plane and identifying the optimal plane and where it's positioned in the feature space. But at the end of the day, it's a simple geometry problem, right? Find a plane that slices through my data and allows me to define bad versus good. And this is, if you understand this, you understand the basic formulation of the machine learning detection problem. You have a feature space, you have a decision boundary, you want to find the right decision boundary that identifies the pattern. Now I want to go from the toy example to, I want to take a couple steps from the toy example towards what real machine learning works in like an industrial context. So real decision boundaries tend not to be planes. They tend to be these wonky, distorted, curvy shapes, right? So this is called a nonlinear decision boundary because it's not planar. So you guys will see in the real examples I show later that tends to be the case. And also in the real world, we don't just use three features. We use lots and lots of features. So in our projects internally at Sophos, we usually define feature spaces that have at least 1,000 dimensions, right? And so when you get up into 1,000 dimensions, you can't visualize things anymore. Here's an example of a 6-dimensional feature space, right? So here, if we add in DLL imports, memory allocations, and sections to our features for Windows binaries, we have a feature space that has 6 perpendicular axes. It's impossible for our minds to really visualize it. Here's an attempt to render the decision boundary in that space. I'm rotating it around just for dramatic effect, but that's a 5-dimensional surface, right? So just to give you a sense of how sort of trippy and when weird things get when you get into these higher dimensional spaces, but you're still really thinking geometrically. But I'm going to stick to lower dimensions in the examples here just to get the ideas across. Okay, so let's get to neural networks now. So you guys understand the basic setup for machine learning, right? You have a feature space, you're trying to find these geometric structures that cut through the feature space to separate malware from benignware. So where do neural networks come in a detection context? Neural networks are just mathematical machines, at least when we're doing detection with neural networks, they're sort of mathematical machines for drawing decision boundaries. So let's look at this setup here. So we have a neural network, right? So these are the input neurons that take features in. So I'm using 2 features here, file compression and file size. We're still imagining that we're in a malware detection context. They sort of go into, that data goes into the neural network. We have layers of neurons, right? Each one of these boxes is a neuron. Each one of these boxes is a neuron. Each one of these boxes is a neuron. And finally, there's an output neuron that you're not seeing here that outputs a 0 to 1 score. And the neurons in this layer are connected to all the neurons in this layer, et cetera, right? So there's lots of connections. Don't worry about exactly what the neurons do for now. I just want to show you how a neural network can generate a decision boundary. So each one of these connections has a weight. So you can think of it, if you want to use the real biological neuron metaphor, you can think of it as like the strength of a synaptic connection between 2 neurons. And the weight is just a number, right? It can range between negative infinity and positive infinity. So if you guys look here, I'm editing the weight, right? Actually, let me stop for 1 second. So I'll show you the pattern that we need to capture here. So the pattern is this spiral galaxy type pattern. So these orange dots are the malware. These blue dots are the benignware. Of course, this isn't real, right? I just made this up to make a sort of complicated pattern. But we want to capture the fact that the malware exists in this inner arm of the spiral galaxy and the benignware exists in this outer arm of the spiral galaxy. This is a hard pattern to capture with a mathematical function, right? So I'm editing the weights here. And as I edit the weights, look at the decision boundary, right? So look over here. you can see changing the weight value, right, changes where the neural network thinks the pattern is. So if I could find the right, so the basic idea is if you think of the neural network as a big Etch-a-Sketch, right? If I find the right, if I sort of tune the weights just right, the idea is I could capture that spiral galaxy pattern and then use that to detect malware. But it's very hard. You guys can see in the video I'm editing the weights and I'm finding it very hard to capture the pattern. So let's talk about learning. So neural networks can learn automatically to capture the pattern. And when we talk about learning automatically, what I'm really saying in a neural network context is a neural network is automatically tuning the weights to capture the pattern, right? So you can see that the weights are changing, right? Because the connection strengths are changing in the visualization, and the decision boundary is changing because the weights are changing. So it's getting closer and closer to identifying the right pattern, and now it's basically got it. And now it sort of stabilizes, right? So this looks a little bit impressive, right? But when you think about neural networks that function in feature spaces of 50,000 dimensions, right? And where there are very complex patterns in the data, right? And so we're working with these very complex geometries. Neural networks excel at capturing patterns in these high dimensional spaces, right? Which is why it's this simple process that led to the result that I showed you earlier in the James Bond film, right? It's really, if you get this, right, you get the basic idea, right, behind how those neural networks learn. This is just a simple toy two-dimensional feature space, but what's really incredible about neural networks is how they perform in high dimensions, and when there's complex patterns they need to capture. I want to say a little bit about how each neuron gets computed. So each neuron is a very simple computational unit. So I'm going to be talking about the most common type of neuron, a rectified linear unit, a neuron with a rectified linear unit activation. This is what most people are using nowadays in machine learning research. And how it works, I would say, is quite simple. So a neuron has a bunch of incoming connections, which are data that are coming out of the neurons that are connecting into it. And then it outputs a single value, and that value gets passed along all of its outgoing connections. So how does it compute its output value? Computes its output value by, for each one of the inputs, it takes the weight of that connection and multiplies it by the input. So if the weight is 5, I'm actually going to compute a few neurons here. I'm not sure how visible this is to you guys. The text is kind of small. I'm going to compute some neurons here. This Python code, it's like 30 lines. It's all the code you need to compute a neuron's activation, right? So what's happening here is I'm passing in some values to the neuron, 5, 5, and 5, and each one of those connections has a weight, and all the weights are 1, right? So I wonder if anybody knows what the output will be. It's 15, right? 1 times 5 plus 1 times 5 plus 1 times 5. And that's it. And the neuron thresholds its output such that if the output is greater than 0, it outputs whatever that weighted sum is. If it's less than 0, it doesn't output anything. And you can think of this very, very loosely and in a very hand-wavy way as mimicking the behavior of biological neurons, right? So biological neurons either fire or they don't, right? If there's not enough energy coming in, they don't fire, right? So in this case, if the strength of the incoming data is not above 0, when you multiply it by the weights and sum it up, then there's no activation, no information gets passed through. Otherwise, all the information gets passed through. So that's basically it. That's the basic neuron that's being used in industrial systems at Facebook and Google and Sophos and Symantec and all the places where people are doing deep learning. And the magic is that when you combine thousands of neurons together in the right architecture, you get the demonstrations that I showed earlier, right? But they're simple units that have these amazing emergent properties when you combine them together. Okay, so let's talk about how weights get automatically tuned through the training process in a neural network. So I'm going to take a breath here because this is complicated if you're not used to thinking in this way. But a neural network has some number of weights, right? So in this example, maybe it has 200 weights, right? And they all have some setting, right? Maybe one weight is 5, maybe another weight is -2. So you can think of the neural network as having a state that lives in, if there's 200 weights, it lives in a 200-dimensional weight space, right? And if we change a weight, right, then it moves a little bit along that axis. That's hard to think about, so let's just think about 2 weights. So here in this slide, right, I have weight 2, that's this connection here, and weight 1, that's this connection here. So I can plot the value of those weights given the current weight setting in this neural network up here, right? So that's the current configuration with respect to these 2 weights of the neural network. Now I have this heat map here. So in the red part of the heat map, the weights are not good. The neural network is drawing a bad decision boundary, right? And you can kind of see that here, right? So in the plot, right, the red is overlapping the blue. We don't like this decision boundary, right? It's not capturing the spiral galaxy structure. So then the question is, how do you tune the weights to get them to be good? You can think of it as moving through space, right? So we're up here in sort of the red zone, and we want to get down here into in this pleasing green zone where we're capturing the pattern. So it looks easy, right, since you see the map and you're like, well, just go to the green zone, right? But the reality is the neural network doesn't know where the green zone is. It just sees I'm up here, and it can see, oh, it's a little bit more green over here, right? And in calculus, it can see sort of that if it took an infinitely small step, it would be more green over here, right? So it just sees sort of a tiny region around. You can think of it in a simple way. It's just a tiny region around where the weights are set right now. And the idea is it just wants to move a little bit towards the green because that's all it can see. It just wants to go that way, right? And the really cool thing is, so if you think of it, that sort of process of just moving towards the greenest area possible, the way the weights are changing when the neural network is learning, you can think of it in the metaphor of like a ball rolling down a hill, right? So here you're seeing weight 1 and weight 2 being changed. The neural network just keeps moving in the area of steepest descent towards the green. And all it can really see is just where the greenest area is relative to its current position, right? And the way neural networks are designed, they're designed in such a way that it's easy to sort of fall down the hill towards the green region. And when it's falling down the hill, what it's really doing is measuring its error on whether or not it's getting its detections right. So in a malware detection context, it's saying, oh, if I was to move a little bit this way, could I have gotten more of those malware detections right in the training data, right? And it just keeps moving along in this iterative fashion. And that's how neural networks get trained. There's a whole class of algorithms around how to roll down the hill. Do you use momentum, right? Do you save some state about, do you back up and go backwards? But the basic idea is sort of a rock rolling down a hill. And this class of methods is called gradient descent or stochastic gradient descent. Okay, so let's bring all of this together. So I introduced the idea of a feature space, right? These are some attributes that you extract in a malware detection context from malware, right? I introduced the idea of a decision boundary, which is a geometric structure that we use to identify the separation between malware and benignware. Introduced the idea that we check what side of the decision boundary we're on in order to detect whether or not a binary is malware or benign. I introduced the idea of neural networks as these mathematical machines for identifying decision boundaries, and I introduced the idea of learning, which is this process of moving through in the weight space, so manipulating the neural network's weights to get the right decision boundary, and how that has this physical metaphor of the neural network moving down a hill in the weight space. Okay, so just bask in the cuteness of these kittens for a second, because I'm like, this is sort of heavy stuff, and it's not over yet. It's not over yet. So, all right, just take a minute. Okay. So I'm going to go one step further and talk about a class of neural networks that's extremely important that we use a lot in our work and security, and which is used also in vision applications and audio processing. A very important class of neural network called a convolutional neural network. So I'm going to start by introducing what convolutional neural networks are not, right? So here's an example of a neural network designed to detect whether or not an image has a building in it or does not have a building in it, right? So in the old days, before convolutional neural networks became the dominant way of doing computer vision, what researchers would do would be to design custom code that extracted interesting features from the image. So how many lines can we detect on the image? How bright is the image? How much contrast is there in the image? How many curves can we detect in the image? How many white blobs are in the image? So there wasn't really good science around what features to detect. Like, should it be blobs or triangles, right? Like, people just sort of came up with this stuff. And lots of papers were written about how to detect blobs or how to detect lines, right? And people would experiment, and then that would get fed into a machine learning system. In the old days, it was usually a support vector machine. Nowadays, neural network, right? And they would train the neural network to detect whether buildings were there or not. The problem with this is that it was very labor intensive, and it didn't work very well. So in a modern context, what we do now, right, is we use a special kind of neuron called a convolutional neuron. And what this does is shown in this animation at the bottom left. These neurons, they scan over the image and they compute their output based on each patch in the image. They're a lot like the neurons I just described, except that they have this scanning property where they scan over looking for features. And they have this special property, which is that they learn as part of the overall learning process what features to look for. So they're automatic feature extractors that are trained to identify good features. So they're trained in the context of building versus no building, right? They're trained to identify features that are good at detecting buildings, right? So a typical computer vision network would use thousands of these neurons, and each neuron would become specialized at detecting a useful feature for detecting building versus no building. These neural networks work way better, dramatically better than non-convolutional machine learning systems, and they're much easier actually to build, right? Because you don't need to do all this manual feature extraction. So there's a connection here with the work that we're doing in my research group. I'll get to it in a little bit, because we also use convolutional neurons in a very different way. Just a couple more things about convolutional neurons in a vision context. So typically, the convolutional neurons are arranged in layers, right? So there'll be an initial layer of a few hundred convolutional neurons which detect features, usually primitive features like lines, blobs. Another layer, so this is an example of a face detector, male versus female, so it's detecting it's a face, male or female, right? So the next layer would detect like eyes, ears, noses, cheeks, chins, beards. The next layer would detect facial archetypes, and then an individual face would be represented as a mixture of facial archetypes, right? And then that information would be the feature vector, right? And it would go into the ordinary neural network, and it would make a decision. That's the overall flavor of how convolutional neural networks work. So the URL detector that I introduced earlier works in quite the same way. So that's a convolutional neural network as well. We're not using convolutional neurons on images, we're using them on character strings. So in the animation that I made here, right, you're seeing this red box. The idea is that's a convolutional neuron. It's being passed over the character string, and it's looking for features in the URL. So the kinds of features it recognizes are like .ru, right, for Russia, or .uk for the UK, or .com, or PayPal, right, stuff like that. The neurons are looking at multiple resolutions, at a resolution of 2, 3, 4, and 5 characters. And what winds up happening is the URL gets represented as a mixture of the patterns that these, in this case, 1,024 convolutional neurons have recognized in the URL. And that gets fed into the rest of the neural network, which decides if the URL is malicious or benign. So we did some introspection into the weights of this convolutional neural network. And it's quite interesting what it learns, right? So this is, in this plot, when letters are close together, this is just a representation of the weights in the neural network, but when characters are close together, it means that the neural network thinks that they're similar. And when they're far apart, it means that the neural network thinks that they're different. And it's interesting, right? Because so the uppercase characters, the neural network decided that they're all similar, right? It also decided that the punctuation marks are similar, decided that the digits are similar, right? You see lowercase letters grouped together here. And it did this all autonomously, right? It decided that I should treat those characters as similar so I can solve the problem of identifying suspicious versus not suspicious URLs. So this is important because it allows the neural network to achieve a really high degree of expressivity. It allows it to be very expressive when it comes to identifying interesting patterns in the character strings, right? So here's an example. Here's a notional example of what one of the convolutional neurons can do, given that the neural network knows that these characters are similar. So it can express ideas like the following: like, if I see an uppercase character, in this region, these are decision boundaries, right? So if I see an uppercase character in this region, followed by a character in this very tight region, followed by this exact character, followed by just a wildcard, so like any old character, followed by a punctuation mark, right? Then I'm going to fire, right? And that's just one neuron out of 1,024. So you can think of this as sort of like a neural regular expression. The neuron can wildcard out characters. It can look for character classes, right? It can look for specific characters. But in a way, it's better than a regular expression because it doesn't just say, did this pattern match or not? It says, to what degree did this pattern match, right? So the neuron will generate an output, a really high output if it matches exactly, and a much lower output if it doesn't match much, and a zero output if it doesn't match at all. So you can imagine if you could mix together 1,024 of these patterns and then run them through a neural network, right? You'd have quite a good URL detector, and that's indeed what we found in our research. Okay, here's just, I haven't talked as much about our HTML detector, but we also, our web detection research also includes a neural network that looks at complete HTML pages and decides if they're malicious or not. So this is also, you can think of this as a convolutional neural network as well. So this neural network takes an HTML page as its input. There's more detail here. You guys can ask me for a link to our research paper if you're interested afterwards. But basically it takes the HTML page as its input, runs it through what we call the inspector, which has convolutional neurons in it. And what the inspector does, you're seeing in this animation. So it looks at the page at low resolution, so it looks at small chunks, larger chunks of the page, larger chunks, and then the entire page. And it collects information about the page. And then what we call the master looks at all of the information the inspector has collected and determines if it's malicious or not. Also determines if it's a phishing page or if it's a drive-by and this kind of thing. And I would say the really cool thing about this is that the entire system, including the inspector and the master, are tuned using that sort of hill rolling process that I described earlier. So everything in the system is trained in concert, right? So the inspector learns to find useful patterns to solve the problem. The master learns to take advantage of those patterns, right? And the inspector learns in conjunction with the master to find patterns that the master is going to find useful. And it takes very little manual work on our part. So we're not parsing out the DOM or any of these kinds of things. The neural network is figuring out structure itself, right, and identifying good ways of detecting malicious HTML pages. And we find that this technology works far, far better than blacklists and signatures, at least in our internal context. We have a paper on this. Let me know if you're interested. Okay, here's another, I would call this a neural network fail. This is a meme generated by a neural network. I'm not sure if you guys get it. I didn't get it. And this is closer, I think. Although this guy looks like he's graduated along, maybe in cat years. Okay. So I also think maybe you guys are tired of hearing about deep learning. Okay, so I'm wrapping up here. So I wanted to talk a bit about the tools that we use in our research group at Sophos. And these are tools that are used generally in academia and also in the industrial security machine learning community. So we use, so I'll start at the bottom here. So we use Linux and we run lots of EC2 instances on AWS. We find that helps a lot being able to, when you're doing machine learning research, it's very good to have elastic compute, right? To be able to scale up to a ton of nodes when you need to do a big research project or train a big model and then scale back down. So cloud computing is important. We use Linux. It's sort of like you have to use Linux to do machine learning research, I think. We write almost everything in Python. When it needs to go really fast, we write it in C++. Some of us do. I'm terrible at C++. We use TensorFlow, which is it's basically an applied math library maintained by Google. It's really good at taking some linear algebra and calculus and sending it down to a whole bunch of GPUs and computing it in parallel. It's a good library, but it's low level. So a layer above that is we use Keras, which is a high level deep learning library, which allows you to really easily define deep learning models. Some of us use another library called PyTorch as well. But we use a high level framework to define our deep learning architectures. That's our basic stack when it comes to neural network research. We also use a bunch of auxiliary libraries. So we use, like Seaborn is a really good statistical visualization library. We use to visualize our results and visualize our data to get a better understanding of the data we're working with. We use sklearn, which is it's the like de facto general purpose machine learning library. It's not deep learning focused, but it has a lot of useful machine learning tools. We use SciPy and NumPy for sort of like linear algebra type stuff and statistical computations, and we use Matplotlib. It's also a very good data visualization library. So these are all, learning to become a security data scientist involves learning these frameworks. They're not that hard, but they're super useful. You're going to need a GPU to do deep learning. It's about 6 times faster to train a neural network on a GPU. GPUs are very good at fast matrix multiplication, which is the staple of deep learning math. So we use GPUs very heavily. Basically everything we do is computed on a GPU when it comes to training neural networks. I just wanted to give you guys a sense of how little engineering work it is to define one of the deep learning architectures I've talked about today. So the complete code for our URL model is here, right? Defined in Keras. It's not a lot of code. The hard part of doing deep learning is not, at least when it comes to defining the neural network, it's not programming. It's the conceptualization of the problem. It's your ability to experiment efficiently and in a savvy way. It's your knowledge of how the mathematical constructs work. But actually defining the model, it's not a big engineering effort, right? It's just that page of code. Some of our models take more, some will take less, but I think this is a dramatic example of how little effort it is from a programming perspective to define a neural network like this. So I think everybody who practices security should become a security data scientist to like a small degree. Because I think that data science is not a fad. I think it's going to be an area in which we're going to need to focus on in the future. Data science is designed to learn from data and process data and make inferences about data and do detections. And security in a way is all about data and identifying patterns and trends and malicious conditions in data. So I think all of you are, data science can look intimidating. Everybody in this room is way smarter than you need to be to understand what I'm talking about. It just takes effort and time and dedication. You have to be, I think, good qualities in the security data scientist are being open-minded. A lot of people I've noticed a lot of people in the security industry come to data science thinking they know, what constitutes malware, right? And like then you start looking at the data and you're like, oh, actually the amount of encrypted data in a binary actually has nothing to do with it being malicious, right? And you need to be open to questioning your assumptions. You need to be curious about questioning your assumptions. You need to be obsessed with improving your results. That's like the only way you can deal with what's sometimes drudgerous work of doing experiments that take a week long to run and experiments not working out, right? I think being really dogged and stubborn about getting good results is just an important quality. And then when you think you get good results, you need to assume that you didn't and that you made an error and go back and figure out what you did wrong. Really important to work with people who are not data scientists, right? So this cyborg is like my way of saying like, a security organization needs to include people who are statisticians and data scientists, but also people who are not and who bring domain expertise to bear, right? And I'm not one of those people who argues that ML is going to replace everything. I think ML is just one tool out of many tools within security, and it's important to work with people who are malware reverse engineers and people who work in SOCs and that kind of thing. All the projects that I've seen have some success have always included collaboration with those types as well. So where to go from here? Obviously buy our book. You can Google it. You can pre-order it if you want. This is a good linear algebra book by Gilbert Strang that I liked a lot. He's, I think, the best linear algebra teacher out there. Linear algebra is like at the basis of a lot of what we do in machine learning. Coursera has a lot of free machine learning courses that are really good, and Wikipedia is heavily used in the machine learning community as like the knowledge base for understanding machine learning algorithms. So with that, I'll wrap up. Here's my email. There's my Twitter. Feel free to reach out if you want background. Any of the projects I talked about, we have research papers on that define them with a lot of exactness and empirical rigor. Feel free to ping me if you're interested. So.